Sergio Morillas from Teledyne E2V. Thank you.
You're welcome.
And looking forward to hearing your presentation about highly reliable 3D imaging for challenging applications with time-of-flight. Sergio, the floor is yours.
Okay, so now, thank you for attending this session about high reliable 3D imaging using time-of-flight. So there are multiple techniques or technologies based on time-of-flight concept, but generally speaking, all of them are based on estimating the distance, measuring the time that the light takes to travel to an object and back. Time-of-flight technologies can be categorized in two main groups. So direct time-of-flight, where distance is estimated by directly measuring light travel time, and indirect time-of-flight, in which the distance is calculated based on the phase of the reflected light pulse. Both techniques have their pros and cons, but I'm focusing today in indirect time-of-flight, since in our view it's more flexible to address a variety of markets, not requiring long distances in the range of 50 to 100 meters, where direct time-of-flight performs better. So quick introduction. So in indirect time-of-flight, normally you need more than one image to compute a 3D image. So I'm showing here an example of a three-phase shifting algorithm, where you have two first phases synchronized with the light with 90-degree phase, and you use the ratio between the charge accumulated in both images to estimate the phase and thus the distance, and then use a third one to remove the background. Time-of-flight applications, time-of-flight technologies have been enabling new applications in the last years in multiple markets. But the thing is that all these markets have very heterogeneous set of requirements, thinking about field of view, distance range, reflectivity range, 3D frame rate, etc., just to name a few. And it's very difficult to segment a closed set of requirements for each market. So we can say that, for example, for warehouse and logistic management, wide field of view is needed, quite short distance, let's say 3 meters to 5 meters, and quite large reflectivity range in order to be able to inspect black rubber, for example, or black gloves worn by the operators. But for pick-and-place robots, longer distance is needed, maybe not so large field of view, and reduced reflectivity range. Whereas for robots for factory automation and for robot navigation, you need to ensure that you can have multiple time-of-flight systems working together without interfering each other. And we can continue like that. So 360 degrees with sunlight robustness for construction and building mapping, etc. And it's even difficult for that same market to find the same applications. So for example, it's not the same at all. Sorting boxes in a belt compared with, let's say, smart filling of long tracks for logistics. It happens the same for automotive. So where you have in-cabin monitoring in-cabin occupant monitoring versus, for example, long-distance pedestrian detection, etc. So having all this in mind and going to the title of the presentation, so what does reliable distance measurement mean for time-of-flight, using time-of-flight? So only perform measuring with high precision, high accuracy? So I think we can all agree that at least not only. So of course, it's critical to measure precisely and accurately, but also you need the right angular resolution, right 3D frame rate. You need to be sure that you can capture dark objects, bright objects at maximum distance, etc. So from our point of view, high reliability is tightly linked with high flexibility in order to be able to address all these markets and applications. And I'm presenting here Hydra 3D, which is one of the most flexible and thus reliable sensors in the market. So talking a bit about Hydra, so it has a spatial resolution higher than the average that can be found in the market. So it has 832 by 600 pixels with 3 taps per pixel, or 3 memory nodes. I'll explain later what's that. With very good near-infrared sensitivity and the modulation contrast. In addition, it's super flexible in the way distance measurement and high dynamic range and similar features can be configured. And on top of that, it incorporates a functionality on chip to let multiple systems to work in the same area without interfering each other. So why 3 tabs? Why is it important to have multiple memories inside the pixel? So if you remember from the introduction, I said that in indirect time-of-flight, you need more than one image to compute a 3D image. So again, I'm going to the example of 3-phase algorithm, and I'm comparing with one pixel having one single tap. So in this case, you need to acquire 3 images. So you shoot your light source once to get to acquire and read out phase 0. You shoot the light source another time to acquire and read out phase 1, and run a third acquisition to capture the background. And only then you can compute your 3D image. So there are 2 things that I would like to highlight here. So first of all is that if you have a fast-moving object during this whole process, then you will get motion artifacts in the image. And in other words, errors in the distance measurement, because you are mixing the information of the 3 phases, and the objects are in different positions in each phase. But in addition, you have had to shoot your light source twice in order to get the 2 phases, the 2 active phases. In Hydra Pixel, since we have 3 memory nodes, you shoot your light source once, and you can get all your 3 phases acquired and read out in parallel, eliminating motion artifacts. And in addition, you have only had to shoot the light source once, reducing the average light power. In this example, we have kept the 3D frame rate constant so that you have lower light power, but you can think of using this extra additional time either to increase dynamic range or to improve precision by making multiple captures. Another key point in time-of-flight is dynamic range. So time-of-flight applications are naturally very high dynamic range applications. And the reason is, one of the reasons is the contribution, the combined contribution of distance range and reflectivity range. So to put an example with a few numbers, so assume you have application 1 with so targeting to inspect objects with reflectivity between 15 and 85%, and in a distance between 0.5 and 6 meters. And then you have application 2 wanting to increase the reflectivity range, for example, because you want to inspect black rubber, as I said before, so it is 1.8% reflectivity. You want to increase bright objects up to 95% reflectivity and extend the distance range up to 10 meters. So in this case, you need more than 25 more times dynamic range for application 2 compared with application 1. So this is large enough to not be able to manage it only with having a big full well capacity in the pixel. And Hydra incorporates a specific functionality to be able to extend the dynamic range as required by the application. We have said at the beginning that flexibility is also super important. So in Hydra, one single trigger launches what we call multiple measuring sequences. So this picture is actually quite simple. So the first section, which is the one rounded with the blue square, is a single 3D acquisition. So you acquire 3 faces and can compute a 3D image. Okay? But inside of one of these measuring sequences, you can have So you can have multiple 3D acquisitions, either to extend dynamic range or to improve precision by averaging, for example. But in addition, with a single trigger, you can launch multiple measuring sequences. And this can be useful to, for example, implement multi-frequency algorithms, multi-range algorithms, or even to interleave 3D and 2D captures within every trigger. So all in all, having this flexibility to manage dynamic range and to configure the distance measurement, which can be even on the fly, is a significant asset to cover as many applications as possible. And I'm showing now a few examples of this flexibility. So this first example is using a single 3D acquisition. So let's say won't be able to manage a big dynamic range, so that is suitable for short distance. But on the other hand, we can reach close to 100 3D frames rate. And as you can see, with total lack of motion blur. This is useful, for example, for in-cabin occupant monitoring application or for high-speed range gating. In this second example, so we are using multiple captures to increase dynamic range. So we are showing a 10-meter configuration with targets between 15 and 88% and 85%, running at 25 frames per second 3D frame rate with no motion blur at all. So useful for applications requiring distances from, let's say, 10 to 15 meters, like logistics, AGV, or construction mapping. And in this last one, so we're illustrating an example of using multiple measuring sequences to cover the same 10-meter range, but using several smaller ones in order to keep the better precision of the shorter distance range. So there is a person coming through that corridor, and you will see that when the person reaches 5 meters, the color scale changes right there. So we have left that intentionally to illustrate when we change from one range to the other. And you can see how swiftly it's done in real time, so with no halting at all. Well, there is a last example, but I don't need a slide for that, so because we have a live demo in our booth. So this is to illustrate the multi-system functionality. So you are more than welcome to visiting us in our booth. You will see there 2 Hydra evaluation kits working at the same time, and you will see how activating this on-chip function in the sensor, you will see how we remove any mutual interference caused by the 2 systems on each other. So finally, so I understand that all this flexibility that I'm mentioning here may sound difficult, but actually it's not so difficult, and we have a team of experts to help you to find your solution. So we have, of course, experts at the sensor level, but also in electronics design, optics, algorithms, time-of-flight modeling, eye-safety modeling, and we have dedicated facilities to test and characterize and explore new applications and to calibrate systems. So please contact us, and we'll be more than happy to help you find the right solution for your application. Thank you very much.
Thank you, Sergio. And also, Wow, I mean, with that much stress running to your booth,
okay.
getting the presentation.
My good friend Pablo around helped me, so.
Still presenting like this, I really admire it. Thank you.
It's okay.
Yeah.
Thank you.
So I don't see any questions, unfortunately. People, you are welcome to ask questions, so maybe tomorrow, yeah? But I have a question to you.
Okay.
100 frames per second.
Yes.
3D frame rate.
Yes.
That really sounds, wow, like a movie. So you mentioned HEVs, you mentioned logistics. So who is your biggest customer, so to speak? Which industry? Is it automotive or?
So not automotive, so we are not an automotive provider. Mm-hmm. So we can explore certainly automotive through partnership, but we are not an automotive provider, so we don't sell Hydra for automotive. Mm-hmm. But some main applications so far, so robotic, beam picking, logistics, so starting to explore ITS as well, so construction mapping. So the ones that I've been highlighting the whole presentation.
Yeah. Okay, so thank you. No further questions, but I guess you are very excited to visit these three persons at their booths tomorrow. And yeah, I would like to conclude this session on 3D. So we started with Teledyne DALSA this morning, we ended with Teledyne E2V this afternoon. So yeah, great.
I'll have a chat with my colleagues.
So thank you for joining this session and have a wonderful evening, and looking forward to seeing you tomorrow at the Vision or here at the Industrial Vision Days. Thank you.